Hello, welcome to another module of this course, Analog Circuits. So, in the past few modules, we have been covering topics on frequency response and frequency compensation. In this module, we shall be studying about an interesting circuit, analog circuit, which is very widely used, and basically they are frequency shapers. So, such a circuit is known as a filter. So, a filter, what it we know what a filter is in our day to day life, but as applicable for analog circuits, the word filter means a circuit that filters certain frequencies, that is allows certain frequencies to pass through it and does not allow certain frequencies to pass through it. So, let us study a little bit more about filters. So, when I say they are frequency filters, what do I mean? Broadly, this filter term filter as applicable for analog circuits can be classified into two parts, active and passive filters. Okay. Now, ideally the frequency response of a filter should be something like this. If suppose Ts represents the transfer function of a filter, then a low pass filter is said to be one which has a characteristics like this. So, here if I call the separation between the pass band and the stop band, I denote that frequency by this term omega c, then omega c represents the boundary between the frequencies that are allowed to pass through that low pass filter and the frequencies which are not allowed to pass through the filter. The frequencies which are allowed to pass through the filter lie in what we call as the pass band, and the frequencies which are not allowed, they lie in the stop band. So, the stop band for a low pass filter, as you can see, is infinite, whereas the pass band is finite. Okay. Similarly, we can define what we call the high pass filter. So, high pass filter, the keywords are high and pass. So, it means higher frequencies will be allowed to pass through such a filter. So, the response again will be the inverse of the low pass filter. This will be my pass band, this is my cutoff frequency, and this is my stop band. So, lower frequencies will be not allowed to pass through the filter and higher frequencies will be allowed. We can obtain various filters by a combination of this low pass and high pass filter. Two such filters are what we call band pass filter and band stop filter. So, a band pass filter So, in a band pass filter, what we have is a frequency response like this. Okay. So, here the first part, if we expand this and this, if we consider only this part, then this is a high pass filter with a cutoff frequency omega 1, and this part, if I represent it by the green marker, this is a low pass filter with a cutoff frequency omega 2, and a combination of the two gives a band pass filter like this. Okay. So, in this case the high pass cutoff frequency is lower than the low pass cutoff frequency. What happens if the high pass cutoff frequency is higher than the low pass cutoff frequency? Then we get what is known as a band stop filter. So, this is a low pass filter, this green line, and this red line represents a high pass filter, and a combination of the two gives a frequency response which is like this. So, it is like, whereas in the, if I go back to the band pass filter for a moment, the band pass filter is a filter which allows a band between omega 1 and omega 2, the frequencies band between omega 1 and omega 2 to pass through. All other frequencies are not allowed. In the case of a band stop filter, it is the reverse. Here we have the band between omega 1, the frequency band between omega 1 and omega 2 not allowed to pass, and all other frequencies are allowed to pass. Okay. Now, in practice what happens is, such an ideal filter is very difficult to achieve. There are some combinations, but that is for later for a higher level course, where we can nearly achieve such ideal responses, but for simple circuits using simple lumped elements, it is very difficult to obtain such ideal characteristics. So, in such cases what we have to get, or what we can realize, is not an ideal filter like that, but a filter with some more frequency limitations. So, in practice what we get is something like this. So, a practical filter will be something like this. So, this is what we call a practical filter implementation. Instead of defining strict pass bands and stop bands where either frequencies are allowed or not allowed, we now define for a practical filter the pass band as the range of frequencies where the attenuation of the signals can be till a maximum extent only. That is, if this is the pass band between DC and omega p, then the maximum attenuation allowed in the pass band is A max, and the stop band we define from the frequency omega s such that the minimum attenuation that has to take place in the stop band is A min. Okay. So, now we do not describe our system in terms of either pass or not passing a frequency. We now define in terms of the attenuation level that should be present in the band. So, for the pass band there should be a maximum attenuation, the attenuation of the signal should not be more than a certain value, and in the stop band the attenuation should have a minimum value, that is, it must have attenuation above the minimum value. So, with this definition of our practical filter, we can start to explore some practical topologies. Now, I must say that between these frequencies omega p and omega s, this is an undefined region. This neither this region range of frequencies between omega p and omega s, they neither lie in the pass band nor in the stop band. Okay. So, let us study some of the properties of the transfer function describing a filter. Suppose the transfer function of a filter is given as now, this is in a polynomial form where the numerator and denominator both are in terms of a polynomial. If we now write in a factor form the numerator and denominator polynomials, then we will get something like this. So, now if we try to plot the poles and zeros of such a system, before that let us suppose that the frequency response of this filter is of this form. Now, suppose the pole 0 placement of this filter is like this. So, you see one thing, that here the response, suppose this is the magnitude is of the transfer function is represented along the y axis, and the, as usual, the frequency is along the x axis. Then you see that in the response, this omega L1 is a frequency. Let me show it like this. Actually, it should be like this. So, you see that at omega L1 there is a dip, and not only there is a dip, but it actually touches 0. Similarly, at omega L2 the response actually touches 0, which means that at omega L1 and omega L2 there should be a 0 present, and not only at omega L1 and omega L2, also at minus omega L1 and minus omega L2. So, that is what we have represented it here. Omega L1 and omega L2 have 2 zeros. Similarly, at minus omega L1 and minus omega L2 we have another 2 zeros. Now, the poles, this poles will, as we already know, since the transfer function, let us go back to the transfer function. This is a polynomial with real coefficients, both the numerator and denominator are polynomials with real coefficients. Hence, the poles will either be real or will be present in conjugate, complex conjugate pairs, and that is what we see here. So, these two constitute one complex conjugate pair. Similarly, these two also constitute one complex conjugate pair, and these two also constitute one complex conjugate pair. Okay. So, also, is there any other zeros present? Yes, there is also a 0 present at DC, which is represented by this 0, okay, that is the 0 at DC, and there is also another 0 present at infinite frequency omega equal to infinity, which tallies with the frequency response, since here the curve asymptotically will approach infinity. Okay. So, these are some important features of in the transfer function of any filter, that how the placement or the location of the lowest values of the magnitude will correspond to the actual placement of the zeros. The other thing that we have to note is this omega p's represent the poles of the system. So, at omega p's the response should be very high. Now, this is seen here, where we see that this omega p1 and omega p2 are actually the two 3 dB frequencies, or I should say they are the frequencies where the maximum attenuation in the pass band is realized. Okay. So, this then constitutes our pass band. The gap between omega p1 and omega p2, that is the frequencies corresponding or the values on the y axis corresponding to the poles, these two poles. Suppose their imaginary values are omega p1 and omega p2, then they correspond to these two edges of the frequency response, and everything else is a stop band. Okay. So, here my stop band consists of these frequencies and these frequencies. So, from here till omega L2 till infinite, and from 0 to omega L1, these are my stop bands. I should correct my definition of the stop band at all frequencies other than the pass band. It is this frequency is from 0 to omega L1 and omega L2 to infinite, but this frequency range omega L1 to omega P1 and omega P2 to omega L2, these are those undefined regions. So, in summary, in this module we saw what a filter is, what are the various types of filter, namely low pass, high pass, band pass and band stop, and also how the location of the poles and the zeros of the filter transfer function correspond to the location of the lower and higher magnitude values of the filter. We usually use the magnitude Bode plot to describe the response of a filter, although for some more sophisticated filters like constant group delay filters, we also consider the phase plot of the transfer function of a filter. So, in this module or in this course, whenever we talk about the filter response, we shall be referring to the magnitude response of the filter. Now, in this module we have seen some general properties of the filter. In the next module we shall be looking at some specific prototypes or some specific functions used to realize specific filters. Also, we shall be seeing later on how these filters, how from a prototype we can achieve specific low pass, high pass and band pass frequency responses. Thank you.